Hello everyone, welcome back. In this video, we're going to talk about a very special type of power series, what we call a Taylor series or a Maclaurin series. What we will soon see is that a Taylor series or Maclaurin series is a way to build our power series essentially from scratch. We will also see that it is an extension of the concept or idea of a tangent line. So far, the kind of power series we've been working with have been kind of alterations or modifications or manipulations of power series for a known function like 1 over 1 minus x, which came from our geometric series. But by extending the ideas behind creating a tangent line, we see that we're going to be able to create a power series from scratch. All we really need to know is the derivatives of the function. So before we write down the formal definition of a Taylor or Maclaurin series, I want to do a quick little review of the tangent lines and an example of finding the tangent line for a function like the natural exponential function y equals e to the power of x. So recall in general that the tangent line to a curve like y equals f of x at a point like x equals a is going to be given by the equation y equals f of a plus f prime of a times x minus a. So f of a gives us the value of our function at the point when x equals a, and f prime of a times the quantity x minus a makes sure that our tangent line has the correct slope of our function at that point, or the correct rate of change of our function at that point. And so I quickly want us to construct the tangent line to the function e to the x at x equals 0. This function is really going to be our guiding example for the general concept of creating a Taylor series or Taylor polynomial. So the two things we really need to create this tangent line are the value of our function at the point when x is equal to 0, as well as the value of the derivative of our function at the point when x is equal to 0. Well, we can just plug in 0 into our function e to the x. We get e to the power of 0, which simplifies to just 1. And we also need to know the first derivative of our function to find the slope of our tangent line. Well, what's nice about this example and our natural exponential function is, well, if we take its derivative, it is equal to itself. So f prime of x is equal to e to the x, and therefore f prime of 0 is going to be also equal to e to the power of 0, or just 1. So putting this all together, we can see that the equation of our tangent line for y equals e to the x at x equals 0 can be written as y equals 1 plus x. And here we've just plugged our information into our kind of general tangent line formula. We have f of 0, which is 1. F prime of 0 is also 1, and technically that's multiplied by the quantity x minus 0. We just don't write x minus 0 because, well, subtracting 0 away from anything doesn't accomplish anything. And so now what we can do is we can compare the graph of our entire function, f of x equals e to the x, to the graph of our tangent line, y equals 1 plus x. And so what we see when we graph both of these functions on the same set of axes is, well, these functions take on the same value at x equals 0, which is going to be the center of our power series or our approximation. And as long as we are pretty close to x equals 0, the difference between our tangent line and our actual function is pretty insignificant. And so what kind of makes this tangent line, and really any tangent line, a decent approximation to a function, as long as we're really close to the point where we made our tangent line tangent to, is, well, the tangent line is going to take on the same value of our function at that point, and it's going to have the same slope or rate of change or first derivative of our function at that point. But we can also see in the graph of any tangent line is that it doesn't have any concavity, so it doesn't really match the curvature of our function at that point or anywhere else for the graph of our function. So in order to improve the idea of a tangent line, we have to kind of add more to it that takes this other information into account. So what we're now looking for is a kind of a piece of information we can add to our tangent line to make it have the same second derivative of our function. Remember, the second derivative of a function describes the concavity of our curve. So our tangent line currently has no concavity involved, but we want to add a piece to our tangent line that gives it the same kind of concavity as f of x equals e to the x at the point of interest when x is equal to 0. So we're now going to improve our tangent line by essentially adding a piece on and creating a new function that is going to be a better approximation to e to the x at x equals 0 and close by. However, what we're going to see when we add this extra piece in is that it is no longer going to be a linear function or a tangent line. Instead, it's actually going to be a quadratic function or a parabola. So we sort of need to notice or observe is that, well, for the general equation of a tangent line, if we plug in x equals a, the second piece disappears and we're just given the value of our function at f equals a. This new piece we're going to add on has to preserve that property. Similarly, when we take the first derivative of our tangent line equation, that constant piece is going to disappear and we're really just going to be left with f prime of a. And that guarantees that our tangent line has the same first derivative or slope of our function at x equals a. So this new piece or term that we have to add to the equation of our tangent line has to kind of preserve those properties. If we plug in x equals a, we still get f of a as the output of our approximating function. If we take the first derivative of our approximating function and plug in x equals a, it has to still give us the same value for the first derivative as our function has at x equals a. And when we take the second derivative of this new approximating function, the second derivative is also going to have to match up with our function we are approximating at x equals a. And so I already spilled the beans just a little bit. The next term we're going to have to add in is going to be a quadratic term. So let's go ahead and start constructing this quadratic term that we're going to add in together. And so it's definitely going to have to involve the second derivative of our function at x equals a. Otherwise, there's no chance for this new approximating function to agree with the second derivative of the function we are trying to approximate at x equals a. We also know it needs to be a quadratic term, just because I kind of spilled the beans on that earlier. And so that means it might look something like x minus a squared, but this isn't quite the entire piece that we need to add in. Because what's going to happen is, well, if we look at what we are trying to add in so far, if we plug in x equals a, this piece will disappear, so we'll still get the value of our function at x equals a. If we take the first derivative of this new piece, well, the 2 from the power rule is going to come out front, and then we'll get 2 times f double prime of a times just x minus a. So if we plug in x minus a, well, then that piece will still disappear and we'll only be left with this middle piece here that involves f prime of a, and that makes sure that the new approximating function matches up with the first derivative of the function we are trying to approximate. However, when we take the derivative of this function, that factor of 2 comes out front and essentially multiplies the second derivative of our function by that factor of 2. And we really don't want that factor of 2 to be there, because when we take the second derivative of this term, well, then it will reduce down to 2 times f double prime of a, and that's giving us 2 times the second derivative value that we want. So to compensate for this, we actually need to divide this new term by a factor of 2. And so now we're ready to add this piece to our tangent line and create a better approximation. So this really is no longer going to be a tangent line, but it's going to be the beginning of our Taylor series, or what we call a Taylor polynomial if we're not doing the entire infinite series. So this new term that we're adding in, this third term, is going to look like f double prime of a times the quantity x minus a squared all over 2. Well, now let's go ahead and do this for our particular example, the function f of x equals e to the x at x equals 0. So the new kind of information we need is really just the value of our second derivative at x equals 0. And well, e to the x is a really nice function to get this process going the first time around, because all of its derivatives are equal to the original function, e to the x. So f double prime of x is equal to e to the x, and therefore f double prime of 0 is equal to e to the 0, or 1. And so we're still starting with our original tangent line to e to the x at x equals 0. That's the equation y equals 1 plus x. But now we're adding on this third term that's going to make it no longer a line, but a quadratic function or parabola. And what's so special about this approximating parabola is it's going to agree with the function at x equals 0, the first derivative of our function at x equals 0, and the second derivative of our function at x equals 0. So looking at our kind of general formula we're constructing here, this new term we have to add in is going to be f double prime of 0 times x minus 0 squared divided by 2, which will simplify to 1/2 times x squared. And well, now we can go ahead and look at the graph of our exponential function e to the x compared to this quadratic function y equals 1 plus x plus 1/2 times x squared. And what we can see is that it is a better fit to our natural exponential function than our original tangent line was. We still have that property where as we get farther away from x equals 0, this approximation is starting to lose its accuracy. But it is still going to be more accurate than the tangent line we started with. And the big idea of why this is now a better approximating function than our tangent line is because it now takes the second derivative of our function into account, which we can interpret as the rate of change of the first derivative, right? The original tangent line has a constant rate of change, but we know for the function, its rate of change is always changing. And what describes the rate of change of the rate of change? Well, that's the derivative of the rate of change, which is our second derivative. And for the rest of the process, we just kind of loop this conversation over and over again. Because, well, when we look at e to the x compared to our quadratic approximation, eventually once we get far enough away from x equals 0, it is going to start to diverge and differ from our natural exponential function. And why does this happen? Well, that's because the second derivative is a constant in this approximation, but we know for e to the x, the second derivative is also constantly changing. Well, what quantity describes the rate of change of the second derivative? Well, that's the third derivative. And that's going to keep happening. Eventually, we're going to add in a new term that takes the third derivative into account, and then that'll be a better approximation, but it won't take the fourth derivative into account. So then we're going to add a term that takes the fourth derivative into account, and so on. So let me go ahead and make a little bit of space over here, and then we'll talk exactly how we take this third derivative into account just by adding in an extra term. All right, so what is this new term we're going to add into our polynomial, this fourth term that is going to take the third derivative into account? Well, just like how we constructed the term that corresponds to our second derivative, we're going to start with f triple prime of a, or the third derivative of our function at x equals a. And just to kind of see the pattern that is currently developing, you might guess that it's going to have a factor of not x minus a or x minus a squared, but x minus a cubed. And so the reason why we work with this factor of x minus a cubed as opposed to some other power of x minus a is because this piece will disappear when we try to plug in x equals a for the original function, the first derivative of the function, or the second derivative of this piece or function. However, by the time we get to taking the third derivative of this new approximating function, we need to have this piece sticking around and being equal to just f triple prime of a. Right? If we think about the original pieces, either in the general form or for our specific example, when we take the first derivative, the first term or the constant term disappears. And that makes our linear term become the constant term. So when we take the second derivative, the second piece will disappear. When we take the third derivative, that third piece or that squared term will then disappear. And so just like with this second derivative term, it's not going to be just the value of the derivative times that quantity raised to the appropriate power. We're going to have to divide it by some constant that just kind of compensates for the fact that we're taking a couple derivatives here. And so if we take the first derivative of our new term to make it kind of fit, it's going to bring down a factor of 3 that we have to cancel out. If we take the second derivative of our term to make it fit, it's going to then bring down a factor of 2 because we're using the power rule to take this derivative here. After the first derivative, we bring the 3 down, and then it'll become raised to a power of 2. For the second derivative, we bring that power of 2 down, and it'll then be raised to the power of 1. So if we take 2 derivatives of what we're looking at here, it will still be sticking around. It'll have a factor of x minus a. So if we plug x equals a into that piece after differentiating it 0, 1, or 2 times, that's going to turn into a factor of 0, which makes it disappear. And that's super important because that preserves the first couple terms of our approximating function and doesn't interfere with them at all. However, when we take the third derivative of this new term or this new approximating function, the first terms will all disappear, and what we'll be left with is the third derivative of just this new term. But after differentiating it 3 times by dividing by this constant factor, what's going to happen is we're going to be reduced down to just a constant function, which will be equal to f triple prime of a. And so this new piece we're adding on is going to end up looking like f triple prime of a times the quantity x minus a cubed all over 3 times 2 times 1. Remember, this product of 3 times 2 times 1 is helping us compensate for all the derivatives we have to take to make sure that this piece disappears when needed to and sticks around when we really need it to for that third derivative, and it makes sure that we get the value of f triple prime of a at that third derivative when x is equal to a. Another observation we can make now is, well, we have another notation for this product of 3 times 2 times 1. we can also write that as 3 factorial. So another more compact way to write this new term is going to be f triple prime of a times x minus a cubed all over 3 factorial. And now we can add that into our current approximation. And so another observation I want us to make that'll help us see how this pattern is just going to continue in this fashion indefinitely is, well, this factor of 2 for our third term corresponding to the second derivative, we can also write with a factorial. 2 is equal to 2 factorial, or 2 times 1. Similarly, this second term that corresponds to the first derivative, we can write as being divided by 1 factorial, since 1 factorial is just a factor of 1. And even this very first term corresponds to just the value of our function, or the 0th derivative of our function, we can put over 0 factorial, since 0 factorial is still equal to 1. And now that we have these first 4 terms for our approximating function on the board, I bet you can guess what the 4th term is going to look like. The 4th term is going to look like the 4th derivative of our function at x equals a times x minus a to the power of 4 all over 4 factorial. But before we write that down and add it to our better approximating function, let's go ahead and find our third degree polynomial approximation to e to the x at x equals 0. So this is really the new piece we have to find, and well, in order to find it, we need to know the third derivative of e to the x at x equals 0, and the third derivative of e to the x is still just going to be e to the x. And just like all those previous terms, when we plug 0 into it, we get a value of 1. And so now our polynomial that gives us an even better approximation to e to the x near x equals 0 is going to look like y equals 1 plus x plus 1/2 x squared. And now we're adding in a cubic term. It's going to be the value of our third derivative at x equals 0 or 1 over 3 factorial, which evaluates to 6, times the quantity x minus 0 cubed, which we can just write as x cubed. And so now if we look at the graph of our natural exponential function e to the x compared to this third degree polynomial, we see it as an even better fit to our curve than our previous approximating polynomials or functions. But once we get far enough away from 0, we see that it is still not going to be perfect, but we can make it even better and always continually improve this approximation by adding in more of these terms that preserve all the other properties of our approximating function at x equals a for those earlier derivatives, and then makes it match up for the 4th derivative, the 5th derivative, and so on. And we're definitely moving pretty fast through this entire concept and video, so I definitely recommend you take the time to actually look at this new third degree polynomial, check out all of its derivatives up to the third one, and make sure it agrees with the value of our function at x equals 0. If we take the first derivative of this approximating function and plug in x equals 0, it needs to give us the first derivative of the function we're approximating, the same for the second derivative of this, and the third derivative of it. And if we add on another piece, it'll have to match up with the 4th derivative, and so on. So now that we see this pattern for building a better approximating polynomial for a function compared to a tangent line, we can take the limit of this process, and that gives us what we call a Taylor series, and a partial sum of a Taylor series is usually referred to as a Taylor polynomial. And so now if we put all of our observations from our guiding example together, we can define what the Taylor series of a function is at x equals a. So this is our definition, and it really just requires that our function we are trying to create this Taylor series or approximation for is infinitely differentiable at the point of interest, or at x equals a. So if y equals f of x is an infinitely differentiable function at x equals a, then we say the Taylor series of our function f at x equals a is given by the following formula. Our function f of x can be approximated by or is equal to f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a times x minus a cubed over 3 factorial. Then we don't have it written there, but it still is there. The 4th derivative of our function at x equals a times x minus a to the 4th over 4 factorial, and so on. So kind of the general or nth term would look like the nth derivative of our function at x equals a times the quantity x minus a to the power of n over n factorial. And we do this forever, and we essentially can continue that process forever, or think of it as doing this as we take the limit as n approaches infinity. And then we can also write this in a more compact form using our summation or sigma notation. And if we do decide to write this using that more compact sigma notation, it'll look like the sum from n equals 0 to infinity of the nth derivative of our function at x equals a times the quantity x minus a to the power of n all over n factorial. Right? We can see that this pretty clearly describes all these later terms, but it still works for those first two terms. This is technically multiplied by x minus a to the power of 0, which is equal to 1, so it just kind of disappears or is not written because it's just a factor of 1. And then we divide these by 0 factorial and 1 factorial, which again just reduce down to 1, and are factors that are not necessary to be written. And so what's really cool about these Taylor series is it really gives us an alternative way to represent our functions as a power series, or basically an infinite polynomial. Another important definition is what exactly is a Taylor polynomial, and it's nothing more than a partial sum of one of our Taylor series. And so the nth degree Taylor polynomial of a function at x equals a is really just the partial sum of our Taylor series. It's usually denoted as something like t sub n of x, and can be expressed as the sum from I equals 0 to n of the ith derivative of our function evaluated at x equals a times the quantity x minus a to the power of I all over I factorial, right? We don't use n here because we're going up to the nth term and we can't reuse a variable twice. Or you could just use these little n's down here and then make this a capital N. The big idea is the nth degree Taylor polynomial is just the sum of the first n terms of our Taylor series. And so unfortunately, I don't have a lot of room on the board currently to write down what a Maclaurin series is. But all a Maclaurin series really is a special type of Taylor series. It's a Taylor series where the center of our series is at x equals 0 instead of some other value like a or 1 or 2 or pi, or wherever we are centering our approximation at. So maybe I'll just make a little note down here so you can see it. If a is equal to 0 for a Taylor series, instead that is referred to as a Maclaurin series, and this just has some historical context and kind of a reference to one of the mathematicians that developed this idea or concept. So we still have up on the board from our guiding example isn't the entire Taylor series for our function e to the x, or Maclaurin series, since it's centered at x equals 0, but it's really like a second and third degree Taylor polynomial approximation to e to the x at x equals 0. So now let's make a little bit of space for our board and then actually find the entire Taylor series or Maclaurin series for our natural exponential function. All right, so let's go ahead and kind of finish our guiding example off by finding the Maclaurin series for e to the x, or our natural exponential function. And what all the Maclaurin series is our Taylor series with a being equal to 0. So in order to construct this Maclaurin or special type of Taylor series, the real piece we really need to figure out is, what does the nth derivative of our function look like at x equals a, or for the Maclaurin series at x equals 0? And for that, we can usually just kind of list the derivatives of our function and look for a pattern. So our function is e to the x, its first derivative is e to the x, its second derivative is e to the x, its third derivative is e to the x, its fourth derivative, all of its derivatives are equal to e to the x. So we can pretty quickly see a formula for the nth derivative of our function is equal to e to the x. And so what that means is that the value of our nth derivative at x equals 0 is going to be equal to e to the power of 0, or equal to 1. So sometimes when we are constructing these Taylor series or Maclaurin series for a function, we find a pattern for the nth derivative for a general x value, then plug the x value of interest in, like a or 0 if it's a Maclaurin series. However, sometimes that pattern can be pretty difficult to observe. So if that's the case, we might often look for a pattern in evaluating the function and its derivatives at the point of interest. So instead of looking for a pattern over here, we actually plug in x equals 0 or x equals a and look for a pattern in that sequence of numbers instead in order to find our general formula for the nth derivative at a or 0. And well, now that we have a nice formula for the nth derivative of e to the x at x equals 0, it's always equal to the constant of 1, we can put that into our formula for a general Taylor or Maclaurin series and see that we can represent e to the x as the sum from n equals 0 to infinity of, well, this is always equal to 1. That's going to be x minus 0 to the power of n, or just x to the n, and that'll be divided by n factorial. And so this is amazing. We now have a new way to represent our natural exponential function essentially as an infinite polynomial. And this infinite polynomial, or the partial sum of this infinite polynomial, can be used for lots of things related to this function, like evaluating the function. So say we wanted to figure out what is e to the power of 1 approximately equal to as a decimal. Well, we could just look at the sum of all these terms when we set x equal to 1. We could do the same for e to the power of 2, e to the square root of pi, anything we want just by plugging in the correct x value. However, just for any power series, we have to make sure the x value we plug in is within that interval of convergence. If we are outside of this interval of convergence, then, well, the series will not be able to be used for an approximation for the function. And the next question we might have for this example to finish it off is, what is the interval of convergence for our Maclaurin series or Taylor series at x equals 0 of the function e to the power of x? And well, remember, one way we can find the interval of convergence of a power series is using the ratio test. So we have to look at the limit as n approaches infinity of the n plus first coefficient of our series divided by the nth coefficient of our series. Well, the n plus first coefficient is going to look like x to the power of n plus 1 divided by n plus 1 factorial. And then we have to divide that by the nth coefficient of our series, which is just going to be x to the power of n over n factorial. And well, we can rewrite this as the limit as n approaches infinity of the absolute value of x to the n plus 1 over x to the n multiplied by n factorial over n plus 1 factorial. And so let's go ahead and figure out what happens with this limit. Almost all these powers of x's cancel out, and we should be pretty used to that by now. So we really just get the absolute value of 1 power of x. And then to simplify what happens with these factorials, well, we have to remember our kind of general strategy for simplifying one of these ratio test problems involving factorials is to take the bigger factorial and strip off some of those larger factors until the smaller factorial shows up. So we'll leave that n factorial in the numerator and rewrite the denominator as n plus 1 times n factorial, and then we can see those n factorials cancel out, and we're taking the limit as n approaches infinity here, so we treat x as a constant, and well, this is like 1 over n plus 1, and that's going to go to 0, and so our ratio test is going to go to 0 no matter what x value we use, and so that means the interval of convergence is going to be all real numbers, and the radius of convergence is infinity, right? We always need to make sure the ratio test becomes less than 1 in order to have x values that work here, and we can see no matter what x value we want to plug in here, it's always going to go to 0, which is definitely less than 1, so our interval of convergence is all real numbers, or from negative infinity to positive infinity. And what that means for us is we can use this Maclaurin series or Taylor series for e to the x for any x value and to figure out basically any value of e to any power. And that's incredibly useful, and it's often how lots of software like your calculator will approximate the value of different powers of e and lots of other complicated functions that we can't just program the values in for. Although technically it doesn't do it for the entire series, it'll just do it for a partial sum. It'll figure out what is the partial sum needed to display all the digits correctly that your calculator can possibly display. And we're going to talk about it in a later video, but there's many other cool properties of these Taylor series. One of them is, well, what we know about e to the x is if we take all of its derivatives, nothing really happens. The derivative of e to the x is equal to e to the x, and that property is actually going to be preserved in the Taylor series representation for e to the x. Like I said, we're going to talk about it in a later video, but if you want to check it out now, try taking the derivative of this series or all the terms in this series, and what you'll see is nothing actually happens. The later term will turn into the previous term, and so on, and it really just stays as the exact same series.